I did not prepare a formal slides talk today because this is a demonstration of an in-class activity. I hope you'll feel comfortable to turn your cameras on, join in, unmute, ask questions, and if not, then I will ask you to participate because it's an in-class activity. So this is a demonstration that I do in my biotransport class. This is a 3000 level class in our BME curriculum that is a required core class. It is typically about 70 students or so in the class. And the biggest situational factor that I need to deal with coming into this class is that students have heard it's hard, it's complicated, and we just got to get through. So that's always on my mind as I'm designing activities for the class. What I find to be one of the most difficult concepts to understand in the class is the ideas behind conservation of momentum. We can talk about mass conservation and keeping track of mass flows in and out of a container or a system boundary or something, but thinking about momentum flowing is challenging as a concept for students. So this demo is just to help students connect conservation of momentum to Newton's second law, because after all, that's all it is. So what I thought I would do, since it's a physical demo and sharing screen will make me so tiny you won't be able to tell what I'm doing, is I thought I would walk us through the activity first, and then I can show you what I put on the board as I go through the activity in a shared slide. Okay? So, welcome. Let's start with, I said this was going to be participatory, so feel free to participate in whatever way works for you. You can use the raise your hand tool. You can type in the chat and I'll try and catch it. Or you can physically raise your hand and I'll call on you, or unmute, or whatever works easiest for you is totally okay. So stomp rockets and tennis balls. I brought my Stomp rocket, although it's not very effective on Zoom as a demo, and my office is small, but I brought it anyway. So for those of you that are not familiar with Stomp rockets, this is a toy where you set up the rocket, which is this red and yellow Nerf-looking thing on the end here, and you set it up with a tripod so you can aim it, you can point it around the room, hopefully not at people. The part in my hand that's purple is an air pocket that you literally stomp on and the rocket goes flying, right? So it's the way it works, since you can't see it, is it creates a pulse of air out of the purple cushion that that accelerates the rocket off the stand. All right, Stomp rockets. So question for the class: what makes the rocket move? Why does the rocket go flying? And it's fun to do while I'm talking. I can have students do it around the room. What makes the rocket go fly?
The air velocity behind it.
Okay, the air pushing the rocket, right? So the air is exerting a force on the rocket. So physics class, physics 1. If I exert a force on an object, what happens to it? Newton tells us that relationship is force equals F equals ma, mass times acceleration. All right, we've seen that in physics 1, okay? Second example, tennis ball, right? So here's my tennis ball, and if I drop the tennis ball, it falls, right? Gravity is causing it to fall. On the Zoom screen, you can't see it falling very far. If I'm standing at the front of a room on a stage and you watch the ball drop out of my hand to the floor, what's happening to the ball as it's falling? The force of gravity is causing the ball to accelerate as it falls to the floor, right? Okay, now also physics 1. In physics 1, we learned about momentum. And if you were going to write down the momentum of an object as an equation, what would you write down for momentum? Mass times velocity. So the momentum of the ball, the momentum of the stop rocket, is mass times velocity, right? Okay, so we just said that the velocity of the Stomp rocket, or the velocity of the ball, was increasing They were accelerating because of a force, F equals ma. We could equivalently say that the momentum of the ball, the momentum of the stomp rocket, was increasing due to a force. Okay, so there's a relationship between the rate of change of momentum and the force that's applied to the object. Newton's second law says so. We're just going to write it down as a rate of change of momentum instead of a force times an acceleration. Okay, let me show you that real quick. Maybe remember how to use Zoom in my old age. Okay, and let me find here. Okay, so we said that the momentum is a mass times a velocity. So a rate of change of momentum is a rate of change of mass times velocity. The mass of the ball, or the mass of the stomp rocket, is a constant. So we can just pull it outside the derivative. And now we have rate of change of momentum is a mass times dv dt, or a mass times an acceleration, which we said is a force, according to Newton's second law, is equivalent to a force. So a rate of change of momentum is equivalent to a force. A rate of change of momentum of the object results from an applied force. Okay, so that's a big important idea. Now, that's if something's accelerating in time, right? If I drop the ball, it's accelerating in time. All right. I don't know how well you can see this. If I throw the ball against a wall, right? Throw the ball against the wall. In the classroom, this is great fun. It catches students totally off guard. I just randomly throw the ball against the wall or bounce it off the floor or whatever works. If I throw the ball against the wall, let's assume for the moment that the speed of the ball when it rebounds from the wall doesn't change, right? I throw it against the wall, it bounces off the wall and comes back with the same speed, just for the sake of argument. Is the velocity constant? Change direction. Velocity is a vector, right? So the velocity changes direction. It's not constant when it bounces off the wall. Now, we said that momentum is mass times velocity. Is the momentum constant when it bounces off the wall? If velocity is a vector and velocity changes because the ball changes direction, that means the momentum changes because the ball changes direction. Now, wait, we just said that a change in momentum, or more specifically, a rate of change of momentum, occurs because of a force acting on the ball. It still works. If I throw the ball against the wall and it bounces off the wall, then the momentum changes because the wall is exerting a force on the ball. We could still say that the ball is accelerated by that force acting on the ball when it bounces off the wall, right? The ball is accelerating. The velocity is changing. It's just changing in direction instead of speed. So we have two kinds of acceleration we can think about. We can think about an acceleration in time. The ball is speeding up as I drop it and it falls to the floor. Or we can think of the ball accelerating because it changed direction when it bounced off the wall. In either case, it's a rate of change of momentum caused by a force. In the first case, we call that a temporal acceleration, acceleration in time. In the second case, we call that a spatial acceleration, an acceleration because it changed direction, even if it didn't change speed. So those should still be captured in our conservation of momentum law. When we come back to class and we write a complicated looking differential equation, that maybe looks like this, and we say this is conservation of momentum, all we're really doing is we're writing down a fancy 3D vector equation that tells us that the sum of forces acting on an object is causing an acceleration in either time or space, or maybe both. So as we get into figuring out how these equations work, what's happening on an object, what's happening on an imaginary point of, or an imaginary box of fluid in a flow or whatever, all we're really doing is we're writing Newton's second law, F equals ma. It's just that we're being more specific about the time and spatial characteristics of what's happening at each point in that flow. All right. So that's the intuitive connection that I want you to remember as we go through the class. All right. So this is the intro activity. This is how I start introducing conservation of momentum. And then we break it down into the pieces and how the math works and things from there. But the goal of this activity is to help students connect from what looks like messy 3D vector equations that are very scary, especially because they have partial derivatives, um, to something intuitive that they can say, oh, that's just a mass times an acceleration. So let me stop there and open it for questions, discussion, ideas. What else would you like to know about this activity?